Okay, so in yesterday's class, we discussed about what is a gear drive or gear, what are the advantages of gear drives. Then we discussed about different categories of gears, that is spur, bevel, helical, and worm gears. After that, we seen some terminology. So in the terminology, especially we need to focus on these three. Basically, in our gear design, we'll mostly probably talk about these three. That is circular pitch, diametral pitch, and module. Of course, this module, circular pitch, and diametral pitch, they are interrelated, but still we need to focus on these definitions also. Maybe in the examination point of view also, they may ask define module, define circular pitch, something like that. So here one thing what you can notice here is, so the notations are important here. So circular pitch is denoted by small pitch, which is given by pi d dash by z, which d dash indicates that it is the gear diameter. Gear, what you can say, pitch circle diameter, because you have a different diameters, but this is corresponding to the pitch circle diameter. That is, you need to remember. Pitch circle diameter. D dash is pitch circle diameter. So Z is number of teeth and D dash is the pitch circle average. So diametral pitch is defined as the ratio of number of teeth to the pitch circle diameter. Then if you take the inverse of this diametral pitch, that is nothing but the module. If you take product of these two, diametral pitch and module, you will get only 1. The product of diametral pitch and modulus is equal to 1 because they are inverse to each other. Similarly, circular pitch multiplied by module is going to be not that one. So these two, if you multiply these two, what you are going to get is 5. The ratio of circular pitch to diametral pitch. So that is 5. So anyway, so you need to remember that. And here I have shown some relation here which is showing the expression for the center distance. Center distance can be measured. Suppose I have two gear wheels which are under mesh. Let us say these are the two gears. Of course, one is pinion, one is called pinion, other one is called the gear. This center distance, this is the distance, what we can call it as the center distance, denoted by small a. That's what I given. So that is nothing but, so this distance. So this distance is nothing but the diameter of this one. If I take this one as a gear, let us say this is gear and this is the pinion. So then this is going to be the radius of the gear. So radius of the gear is given by dz by 2 and this distance. So this is nothing but the radius of the pinion, which is nothing but diameter of the pinion divided by 2. So now if I add dp by 2 plus dz by 2, of course we are talking, if you want to take it as a pitch circle diameter, we are using this apostrophe symbol for that. So use that. So dp plus dz by 2. So that's what we written here. That is the center distance. And you have a relation here for pitch circle diameter and also number of teeth. I think that is defined in the maybe the earlier slides. If I go back one more step here. Velocity ratio. Okay, this is also important. We'll talk about the velocity ratio, which is nothing but the velocity of the driving gear divided by the velocity of the driven gear. So that you need to remember. And then Topland, okay, pitch circle diameter, addendum, okay, dedendum, okay, clearance, base width, fillet radius, toe space, working depth, center distance, and okay. So this is also important. They may ask define pressure angle. So pressure angle is nothing but angle at which the pressure angle is the angle which the line of action makes with the common tangent to the pitch circle. So that is denoted by alpha. Then okay, these are all of academic purpose only. We are not okay. Anyway, that is not there. But if you recall your fundamentals of kinematics, there you studied. So this diameter is nothing but, for any gear, the pitch circle diameter is nothing but module multiplied by the number of teeth, m into z. So this is also you need to remember. So once you know that relation, so using that relation, diameter of the pinion can be written as module times the number of teeth on the pinion plus module times number of teeth on the gear is nothing but the diameter of the gear. So if you know those two things, you can calculate the center distance between the gears. Okay, right. So now with this terminology and notations, next we move on to the force analysis of a gear train. So in that, so we consider a gear train which is subjected to or which is transmitting some power. So therefore, the power, because of this power transmission, the gears are subjected to some force. So that force also, because the force is exerted by the tooth of the driving gear on the meshing tooth of the driven gear. Since here you can see that due to gradual engagement and disengagement of the teeth, the power is transmitted from the driving shaft to the driven shaft. So this is the center of the driven shaft and this is the center of the driving shaft, or this we will call it as pinion, which is driver, gear, which is the driven member. So now here the teeth are in contact, or teeth are in mesh with each other here at this location. So now here, since the driver is rotating, so then this gear tooth will exert a force on the driven gear at the gear tooth. So therefore that means the force is transmitted here, and the magnitude of that force will take it as Pn, and the direction of that force is always act along the pitch line, so pressure line. So that is what we need to know. Figure shows that tooth of the driving pinion exerting a force Pn on the tooth of the driven gear. So here it is exerting a force, driving gear exerting a force on the driven gear, and the magnitude of that force is Pn. According to the fundamental law of gearing, this resultant force always act along the pressure line. So always along the pressure line. So this is the point. So or else you can say this is going to be the tangent common normal. Common tangent. This is the common tangent to the both the pitch circles, and this is the common normal. So always will act along the pitch pressure line. So that is the important point what we need to remember. So but here we can resolve this force, resultant force Pn into two components. So that's what he has shown it here. Suppose if this is by resultant force, that can be resolved into two components. One is acting in the radial direction, that means along the radius of the gear, and other one is perpendicular to the gear. So then the force which is acting towards the radial, towards the center of the gear, we call it as a radial force, and which is denoted by PR, and the force which is tangential to the diameter of the gear, then we call it as a tangential force. So that means this Pn is resolved into two components. One is a radial component, other one is tangential component. But the component of the force which is responsible for the transmission of the power is Pt. The transmission of power is due to this Pt value only. This PR going to exert a reaction on the bearings or on the shaft here. Whatever you have, this PR is going to exert a reaction on the shaft, whereas this Pt is the useful component of the force which is going to be used in the power transmission. So because of this Pt only, the power is transmitting. So that's what I shown it here. The resultant force Pn can be resolved into two components, tangential component Pt and radial component PR at the pitch point. So this is the contact point of those two gears. So that point we call it as a pitch point. If you resolve that force, you have a normal component as tangential component. So this is the tangential component and this is the normal component. And if you know the pressure angle is alpha, you can easily write the expressions for Pt and PR. So Pt is nothing but here, this is the angle. So this is our resultant force. This is the alpha. Pt is nothing but Pn cos alpha. And similarly, your PR is nothing but that is radial load, which is Pn sin alpha. But our intention is always we want to write Pn in terms of Pt, PR in terms of Pt, because the Pt is the useful component which is responsible for the power transmission. So the tangential component Pt is useful load because it determines the magnitude of the torque and consequently the power which is to be transmitted. So the Pt is going to be the useful component of this Pn, which is responsible for the power transmission. Then the radial component PR is a separating force. So that means you can treat this one as something like a separating force also. So one gear it is acting like this, other gear it is acting like this. So then they are acting towards the gear. These two forces are acting towards the gears. So that means it is separating these two gears. So you can call it as a separating force also, which is always directed towards the center of the gears. So always this PR is acting towards the center of the gear. The torque transmitted by the gear is given by, so we know the formula for the torque. If P is given to you, then you can easily calculate the torque. Torque is nothing but MT is nothing but 60P divided by 2 pi N. So that's what I written here. But if I want to substitute P in kilowatts, so that's why I written here kilowatts, then I need to multiply this one into 10 power 6 so that I'll get this torque in Newton mm. So I'll get the units for the torque as Newton mm. So therefore I need to multiply this one by 10 power 6. Therefore the torque transmitted is given by MT is equal to 60 into 10 power 6 by 2 pi N, where N is speed in RPM. You have to take N should be in RPM. So this is the expression for the torque. But so like we already discussed, this Pt is the responsible for this torque transmission. So now torque due to this Pt is nothing but this Pt multiplied by the radius of the gear. If you take R radius of the pinion, whatever you want, you can consider it. So if you take that, you will get the torque expression. So where MT is the torque transmitted by the gears and Kw is power transmitted by the gears in kilowatts, N is speed of rotation in RPM in this expression. The tangential component Pt acts at the pitch circle radius. So you can clearly see that it is acting only at the pitch circle radius. Then the expression for this torque is also given as Pt multiplied by the perpendicular distance, that is nothing but pitch circle radius. Pitch circle radius is nothing but d dash by 2. Or else from this we can write an expression for the Pt. Pt is nothing but the tangential component of the resultant force which is acting along the pressure line. So 2 into mt by d dash. If you rewrite this equation, you will get this. So and also if you want to write an expression for PR, I already written PR is nothing but Pn sin alpha. I written like this. But if you want to write this one in terms of Pt, so I written the expression for Pt also. What is Pt expression? Pt is nothing but Pn cos alpha. So now from this I can substitute for Pn. If you want to substitute for Pn here, Pn is nothing but Pt by cos alpha. So I can substitute something like that also. Pt by Pn is nothing but Pt by cos alpha into sin alpha. So we know sin alpha divided by cos alpha is nothing but tan alpha. So that's why we get PR is equal to Pt sin alpha. So like this also we can write the relations for between Pn, Pt and PR. Okay. So only thing you need to remember is Pn is the resultant force. This is the resultant force and tangential force. So horizontal force is going to be Pt and this Pt will make an angle alpha with the Pn. So that is you need to remember. So then this is going to be your PR. So you need to remember like this. Okay. Right. So this is how you can calculate the radial and tangential loads on a gear tooth when it is transmitting a torque MT. So the resultant force Pn is Pt by cos alpha. So I already shown to you. So then we'll move on to the, once you know the force analysis, that means how much force is transmitted to the gear tooth because of this meshing or because of the power transmission. So there are two components. One is radial, another one is tangential. So the tangential component is the useful component which is contributing towards the power transmission. So radial force is going to be a separating force which is going to exert the reactions on the bearings of the gears or on the shaft. Okay. So next, what are the different types of tooth failures? We'll discuss that. Then after that we'll move on to the strength analysis of gears. So generally there are two basic modes of gear tooth failures. One is failure due to static and dynamic loads. So that means the gear tooth may be failed because of breakage. It's breakage and the breakage is happening due to the excessive load. The load may be either static load or dynamic load. So two kinds of loads we consider. So sometimes we'll consider only static load, sometimes we'll consider dynamic load also. That is nothing but modification for the static load only. So if you modify static load, you'll get dynamic load. So that means because of excessive load, the tooth may be break out. So that is one kind of failure. The other kind of failure is surface destruction. So that means the surface of the gear tooth is destructed. So that means it is a kind of a wear. So that means one is the strength failure, another one is the wear failure, what you can say. So those are the two basic failures. So if you are able to manage or if you are able to design the gear properly, that is by choosing the gear parameters, especially the module and face width, we'll call it face width, which is denoted by B. We already defined what is face width. So if I have a gear tooth, something like this, I have a pitch circle line, something like this. If I extend this one in the third direction, so this I'll call it as face and this one I'll call it as a flank. Then this is going to be the face width. So whatever this distance is there, this will call it as a face width. I think I can show it to you, that figure also. That is going to be clear. See, you can see clearly here. So this distance is going to be the face width. So this is the face we call, and this width we call it as a face width. So if you are able to determine or design the gear with proper parameters of like module and face width, you can avoid the failure of these things. That is failure of or breakage of the tooth because of the excessive load. But coming to this one, surface destruction, there are different kinds of failures. So one will see what are those failures one by one. So the complete breakage of the tooth can be avoided by adjusting the parameters in the gear design, such as module and face width, so that the beam strength of the gear tooth is more than the sum of static and dynamic loads. So that means while designing in order to avoid the breakage of the gear tooth because of the excessive load, while designing the gear itself, we need to choose such that the module and face width are, if you choose the proper values for module and face weight, then the strength of this gear tooth is more than the sum of the static and dynamic loads. Then in that case, you can completely avoid the breakage of the tooth. So if the failure is gear tooth failure because of the static and dynamic loads, if that kind of failure is there, that can be easily overcome just by redesigning or proper designing the gear with appropriate module and face width. Appropriate module and face width. That means the design of gear is nothing but just you need to identify what is the module and what is the face width. If you specify that, then your design of the gear is over. So to design that, what are the factors you need to consider? You need to consider both static as well as dynamic loads. Okay. So that is the first kind of failure. Then coming to the surface destruction, we have different kinds. Like I told, the surface destruction or tooth wear, we call it as a tooth wear. Surface destruction is nothing but tooth wear is classified according to the basis of their primary cause. So what are the factors which are causing this wear? This surface destruction is classified into different categories. And those principal types of gear tooth wear are, first one is abrasive wear. So I think the name itself suggests that it is a wear due to abrasion. So whenever foreign particles in the lubricants such as dirt, rust, weld, spatter or metallic debris can scratch the tooth surface. So these are all foreign materials. So which are not wearing materials. So if these kind of foreign materials are present in the gear on the gear tooth, they try to scratch the tooth surface. Because of the scratching, they were wearing off tooth takes place. That kind of wear we call it as a abrasive wear. So then, to avoid this kind of abrasive wear, the remedies against this type of wear are provision of oil filters, increasing the surface hardness, and use of high viscosity oils. So here, in order to avoid abrasive wear and a gear tooth profile, if you use oil filters for the oil, so therefore, while in the lubricants, so foreign particle in the lubricant can be avoided, such as the rust, water, weld spatter, or metallic debris, whatever it may be, you can avoid it so that you can reduce this kind of abrasive wear. Then a thick lubricating film developed by these oils allows the fine particle to pass without scratching. So that means if you use thick lubrication also, then the lubrication can reduce this scratching or this abrasive wear. So these are the two remedies, possible remedies to reduce this abrasive wear. So then we have next kind of wear, that is corrosive wear. Next kind of one is corrosive wear. So this is due to corrosion. The corrosion of the tooth surface is caused by the corrosive elements such as extreme pressure additives presented in the lubricating oils and foreign materials due to external contamination. So if we avoid this contamination of gear tooth with the external particles or foreign particles which are responsible for this corrosion, then you can avoid this corrosive wear also. These elements attack the tooth surface, resulting in fine wear uniformly distributed over the entire surface. See, if you see abrasive wear, that is pertaining to the some localized space. So it is not throughout the tooth surface. So wherever scratching is happening, there only you have abrasive wear. Whereas this corrosive wear it is distributed phenomena. So it is going to be distributed through the entire teeth surface. So therefore, this is more dangerous when compared to the abrasive wear. So now, if you want to look at the remedies for this kind of corrosive wear, remedies against this type of wear are providing complete enclosure for the gears free from external contamination. So that means complete enclosure means we need to provide a proper gear box. So that's why you can see wherever you have a gear trains are there, those gears are provided with a proper gear boxes. So that is the gearbox will cover or it will separate the gear train from the external contamination. And not only that, selecting proper additives and replacing the lubricating oil at the regular intervals will reduce the corrosive wear. Then next type of the failure. All these are causing the failure. Where you can see all these things is where is nothing but warring up of gear tooth profile. So it is wearing out the gear tooth. So this is also another kind of that wear phenomena. So which we'll call it as initial pitting. So pitting is nothing but a localized phenomena. Again, this is also a localized phenomena. So in the initial or corrosive pitting is called localized corrective. Not corrosive. Initial or corrective pitting is called localized phenomena. Is a localized phenomena characterized by small pits at eye spots, such as eye spots are progressively worn out and the load is redistributed. So here this is nothing but pitting is nothing but you can observe in a gear tooth when there is a small pits are developed at some localized places where you have a eye spots. So that kind of phenomena, what we call it as a initial fitting. Initial fitting. So this initial fitting is caused by the error in the tooth profile, surface irregularities, and misalignment. So this is due to the misalignment, surface irregularities, and errors in the tooth profile. That means if the involute is not properly cut for the gear tooth, then we have a error in the tooth profile also. Because of that, we have this initial fitting. That is one type of localized bay where the tooth profile is not correct, or where there is error in the tooth profile. So if it is not exactly following that inverted curve, then definitely there is an error. Due to that, you have interference and undercutting, that kind of problems are there. That will call it as some sort of a fitting. The remedies against this initial fitting are precise machining of the gears, adjusting the corrective alignment of the gears so that load is uniformly distributed across the full face weight and reducing the dynamic loads. So these factors will reduce this initial fitting. Then next kind of failure is destructive fitting. So this is the one more thing is there, I think. So destructive fitting is a surface fatigue failure, so which occurs when the load on the gear tooth exceeds the surface entrance strength of the material. So now here this destructive is corresponding. So we know that gear tooths are subjected to fatigue life because they are engaging and disengaging. Continuously engaging and disengaging means, so for some time there is a load, for some time there is no load on that gear tooth. So therefore it is a fatigue kind of thing. The load is not a static load here, it is a fatigue load on the gear tooth. So suppose if the entrance strength of the material is less than the fatigue load which is acting on the gear tooth, so then there is a wearing off tooth is there. So that kind of thing we will call it as a destructive fitting, which occurs when the load on the gear tooth exceeds the surface entrance strength of the material. This type of failure is characterized by pits which continue to grow and result in complete destruction of the tooth surface, and in some cases even premature breakage of the tooth. So that means, so this destructive means the name itself suggests that it is going to be somewhat danger. Without notification, the tooths are going to break. So that is what we call it as a premature breakage. So therefore this is going to be the dangerous one when compared to the others. Destructive fitting depends upon the magnitude of the contact stress which is given by X and the number of stress cycles, because it is a fatigue kind of thing. So we need to count the number of cycles and also the magnitude of the stress or amplitude of the stress to be precise. This type of failure can be avoided by designing the gear in such way that the wear strength of the gear tooth is more than the sum of static and dynamic loads. So this destructive fitting can be avoided by designing the gear such that the wear strength of this gear should be more than the sum of static and dynamic loads. The surface entrance strength can be improved by increasing the surface hardness. This is the second thing. Second thing is you can improve the surface hardness, entrance strength by increasing its surface hardness. So which can be expressed either in terms of Brinell hardness number. Generally, the surface hardness can be expressed in Brinell hardness number. So then we are seeing two things. So that is here to avoid the wear. So we already seen that there are two categories of failure broadly. First one is breakage due to the excessive loads, excessive static and dynamic loads. That can be avoided by choosing the proper values for face width and module. And also here also the other kind of failure is wear. Even that wear failure also can be avoided by proper designing the gear such that the wear strength of the gear should be more than the sum of static and dynamic loads. So first you need to calculate what is the sum of static and dynamic loads. Even in the earlier criteria also it is sum of those two loads only. So you can see that here the sum of static and dynamic loads. So now you need to calculate what are the static and what are the dynamic loads on the gear. So then based on those loads only we need to design the gear. So that we'll see the next I think the next slides we'll have that kind of thing. So before that, you have another kind of wearing phenomena which is called scoring. So these are all similar. Maybe in magnitude wise there may be a difference, but they are all similar. Scoring is also nothing but some kind of scratching only. But the factors which are causing the scoring is different. So abrasive wear, the foreign metals are rubbed against the gear tooth surface, we call it as a abrasive wear. But here excessive surface pressure, high surface speed and inadequate supply of the lubricant, so results in breakdown of oil film. See, like I said, it is related to the surface only and the breakdown of the oil film. Because of these parameters, if the oil film is break down, this results in excessive frictional heat and overheating of the meshing teeth. Scoring is a stick slip phenomena. So here, because of the friction, it is a stick slip phenomena in which alternate welding and shearing takes place rapidly at high spots. So here the rate of wear is faster. So in all the case, compared to the abrasive wear and that corrosive wear, the wearing is going to be faster in case of the squaring. Because of this is going to happen because of the breakdown of this oil film, and there is a excessive, when the oil film is break down, there is a excessive heat or overheating of the meshing teeth will take place. So because of this overheating, so there may be a welding stick slip phenomena. Means the gear tooth extent is to the extent part or maybe surface, it is going to weld, and at the same time the separating the load is acting on the gear which is going to separate it. So that means it is welding and separating. So that's what we call it as stick slip phenomena, in which alternating welding and shearing takes place. Here welding and shearing will take place rapidly at high spots. So therefore this is going to be very faster. The wear is going to be faster in case of this scoring. So these are the common possible failures of this gear tooth. So then, okay, scoring can be avoided by selecting the parameters such as surface speed, surface pressure, and flow of lubricant in such way that the resulting temperature at the contacting surfaces is within the permissible limit. So that means in order to avoid that welding, so that stick slip motion, you have to make sure that all the parameters like surface speed, surface pressure, and flow of lubricant is sufficient, which will result in a temperature which is less, and also the contact surface which should be within the limit. Less, we cannot say it is less, so it should be within the specified permissible limits. Then we can avoid this scoring. The bulk temperature of lubricant can be reduced by providing pins on the outside surface of the gearbox and a fan for the forced circulation of air over the pins. So here, if there is an excessive temperature, you can dissipate that excess heat either in the form of a pins by providing the pins. So that is a free convection, or else using forced convection, that is using of a fan. By using a fan, you can circulate for air with some force over those fins. So through that also heat can be taken out from the surface. So by this way you can keep the temperature within the limits so that scoring can be avoided in the gear tooth. Okay, right. So that is about the gear tooth failures. So now we'll talk about the important thing here. So far we say the criteria for the designing the gear is you have to calculate what is the static and dynamic loads. So to estimate that first thing is we want to estimate what is the static strength. That static strength we call it as a beam strength of the gear tooth. So why we call it as a beam strength? Because in order to determine the load acting on this one. So now if I take one teeth, so the tangential force is acting on the teeth is something like this. Just now we've seen the tangential force is nothing but perpendicular to the line joining center to the pitch circle of the gate. So therefore here it is going to act something like this. If I take the tangential force is a distributed force, something like this. Now since the gear tooth base is fixed to the root here. So you can assume this one as a something like a cantilever beam. So this end is fixed. Here you have a load. So we can call it as a some kind of a cantilever beam. Because of this, at this location there is a bending moment. This PT will create a bending moment here, and also it will induce a bending stress. So that's why we call it as a bending strength of a gear tooth. The analysis of bending stresses in gear tooth was done by Wilfred Lewis in his paper. The investigation of strength of gear tooth submitted at Engineers Club in 1892. So this analysis is done by this person Lewis. That's why we call it as a Lewis beam strength equation also. Whatever equation he derived it based on this beam strength, we call it as a Lewis equation. So he has done this analysis for the bending stresses in 1892. So centuries back, but still even nowadays also people are using these equations to identify the strength of the gear tooth, especially not gear tooth. Even today, Lewis equation is considered as a basic equation to design of gears. In the Lewis analysis, the gear tooth is treated as a cantilever beam as shown in figure. Like I said, so here the tooth is fixed here, assumed as fixed here, and this end, this is free. There is no support at this end, so we can call one end is fixed, other end is free, and it is subjected to a transverse load here. The load is acting in the transverse direction, so we can call it as a cantilever beam. Then the tangential component PT causes the bending moment at the base of the tooth. So this is the base. So at this base, it will cause a bending moment. Due to that bending moment, there is a bending stress. So then he made some assumptions in that Lewis equation, whatever he derived. So in that equation, there are some assumptions. What are those assumptions? The effect of radial component, which induces compressive stresses, is neglected. So we already seen there are two forces acting on the gear. So one is a tangential force, other one is on the face width. This will act something like this, radial component of the force. So but in his Lewis analysis, this radial force is going to induce a compressive stress, but it is ignored or it is neglected. So it's not considered the effect of the radial load. So if you consider radial load, again there is a difference in the magnitude of the bending stress, but he ignored that. Then next stage of stage, it is assumed that the tangential component is uniformly distributed over the face width of the gear. So like I said, this PT is assumed as a uniformly distributed load, but in practice that is not true. But still it is an assumption. So by making that assumption, he made the analysis simpler. So this is possible when the gears are rigid and accurately machined. So if the gears are rigid and accurately machined, then only it is possible. But in practice, which is not true. But still, to make the analysis simple one, he assumed like that. Then the effect of stress concentration is neglected. So this is also another assumption. So here you have something change in the geometry. You can see the gear tooth profile. It is going to be something like this. Continuously there is a change in the cross section, but whenever there is a change in the geometry, you have a stress concentration, but he neglected the stress concentration also. Then it is assumed that at any time only one pair of teeth is in contact and takes the total load. So that means where the two gears are meshing with each other, he assumed that there is only one pair. So that means one teeth on the pinion and one tooth on the gear is in contact with each other and they will take the total load. But in practice that is not the case. So the minimum contact ratio is going to be 1.5. So that means, so you can take contact ratio as 2, but you assume it as only 1. You assume it as only 1. So if it is a 1.51, then distribution of load is going to be the difficult thing. Which teeth will take more load and which teeth will take less load. So therefore, if you take only one teeth means, even though the load is total load you are considering for the one gear means it is taking the lesser load than the design load. So therefore, your design is going to be safe. But the only thing is the tooth profile is tooth dimensions are going to be the larger one. That is the only thing. So there is no danger in assuming this one also. So those are the assumptions what he made. So radial component is neglected, the effect of radial component is neglected, radial load is neglected, and a tangential component of the load is distributed uniformly throughout the gear tooth, and effect of stress concentration is neglected, as well as only one pair of tooth is in contact and the total load is taken by only that pair, one pair. Okay, so with this assumption, we'll try to derive what is the expression for beam strength. So now, again, like I said, the cross section is not uniform, so that's what is written here. It is observed that the cross section of the tooth varies from free end to the fixed end. So this is the fixed end and this is the free end for a gear tooth. So then the cross section is going to vary something like this. It is not constant. So but to make it simplified for the analysis, what it is, he consider a parabolic tooth. So that means this is the actual tooth, but he has not done the analysis for the actual tooth. He constructed a tooth with a parabolic profile. So here you can see the profile is something like this. This dotted line shows that profile. The parabola is constructed with the tooth profile and shown as a dotted line in the figure, in this figure. So the advantage of this parabola is wherever you take that, it is going to be having a uniform strength. That means the stress is same at any location. So even though your area is changing, the stress is going to be same. Because with this profile, so from this point, why it is stress is going to be same here? From this point, at this point, there is no bending moment at all. The bending moment is zero. So how we got the bending moment? PT multiplied by the perpendicular distance. The bending moment is maximum at this location and it is zero at this location. So zero means there is no stress. If there is no bending moment, there is no stress. So I don't require any thickness at this location. That's why he zeroed the thickness at this location. But here the perpendicular distance is maximum at the base at this location. So therefore here there is a maximum bending stress. So here I should have a maximum thickness. So in order to provide zero thickness here and maximum thickness here, he modified the profile something like this, a parabolic manner. So that the stress is going to be same throughout the tooth height, whatever you call it as height of the tooth H. The advantage of this parabolic outline is that it is a beam of uniform strength. Uniform strength means everywhere the stress is going to be same. The stress at any cross section is uniform or same. The weakest section of the gear tooth is at section XX, where the parabola is tangent to the tooth profile. So the weakest section is going to be this section XX. Why this is section XX is going to be the weakest? Because here you have a maximum bending moment. Your maximum bending moment PT into this perpendicular distance is maximum here. PD remains same, but at this point it is zero. Perpendicular H is zero here. If I move away, this is going to be the farthest point. So here you have a maximum H value, or indirectly you have a maximum bending moment. So at section XX, the bending moment is nothing but PT into H, that we know. And he has taken the cross section is something like this. If I have a rectangular cross section at this base, only at this location, not the throughout here, at this location, if the cross section having face width B, we'll call it as this face width P, and thickness is height is H and thickness is T. So this one is this diamond. Okay, here I have shown it here. Thickness is tooth thickness is T and face this one is B. Then height is H. So then I can write for a rectangular cross section, the moment of inertia is nothing but BT cube by 12. And also for a rectangular cross section, you have your centroidal axis is exactly center. So the bending stress is maximum at the outermost layer, which is located at a distance of T by 2. So which is located at a distance of T by 2. So now if I substitute these parameters into this equation, what I'll get is the bending moment. Okay, so this is my expression for the bending stress. Bending stress is nothing but mb by I into y. So now I'll substitute this mb, I and y into this, so that I'll write an expression for the bending moment. So bending stress. The bending stress is given by mb is nothing but P2 and H, I is nothing but bt cube by 12, y is t by 2. So if I see rearrange this equation, it is going to be something like this. So from this equation, I'll write pt. So why I am writing pt? Because this is the component which is responsible for the power transmission or torque transmission. So therefore, pt is equal to, if I rearrange this equation, I can write it as b into sigma p into t square by 6h. So in this again, if I multiply the numerator and denominator by module m, so that's what he did. Multiplying the numerator and denominator by the right hand side by m, resulting equation is, here I multiplied, here I denoted. So it remains m only. But the expression for pt becomes mb sigma b into t square by 6hm. So this t square divided by 6hm is denoted by capital Y. And he denoted this one as a capital Y, and this is called Lewis form factor. This Y is called the Lewis form factor. It depends upon the teeth. See, you can see the T is going to be the thickness of the teeth, and H is going to be the height of the teeth, and M is the module. M is the module of the gear teeth. So it depends upon the teeth. So this Y value will vary from teeth to teeth. So that's why he denoted that one as some factor called Lewis form factor Y, which is denoted by Y. Defining a factor Y is equal to t square by 6hm. This pt can be written as now. Pt can be written as mb sigma b into y. M into b into sigma b into y. So in the above equation, y is called Lewis form factor, and this equation gives you the relationship between the tangential force and the corresponding stress sigma b. So now this equation will give you the relation between pt and sigma b. So when you can, from this equation you can clearly see that if pt increases, sigma b also increases. If pt decreases, so for a given tooth, all other things are constants. Even this is the tooth factor which is constant, face width is constant, m is constant. If we increase the pt for a given tooth, then this sigma b is also increases. So that means here the magnitude of the bending stress will depends upon this pt value. So therefore, if I have a sufficient strength for this one to withstand this bending load, then the design is going to be safe. So that's what we say, when the stress reaches the permissible magnitude of bending stress. So that means the load which corresponding to this permissible value of the sigma b, or the allowable value of sigma b, the value of pt corresponding to that, we'll call it as this beam strength. The value of this pt which corresponding to the permissible value of the sigma b, then we'll call this pt as the beam strength or Lewis beam strength, because it is derived by that person Lewis. We'll call it as a Lewis beam strength equation. So this equation, so then since we are talking about the strength, generally we'll use symbol S for the strength. So S YT is for the yield strength, and SY is the shear strength, something like this. So now we'll replace this PT also by SB. So that is S is for the strength and B for beam. So beam strength is denoted by SB. Then I can write SB is equal to M into B into sigma B into Y. So that's what I written here. Therefore, beam strength SB is the maximum value of the tangential force that the tooth can transmit without bending failure. So this is the definition for this beam strength of the gear tooth. So it is the maximum value of the tangential force that the tooth can transmit without bending failure. We consider only the bending failure. We are not considered any wear here. Replacing PT by SB, then the equation can be modified as SB is equal to M into B into sigma B into Y, where SB will call it as a beam strength of the gear tooth, which is expressed in newtons. Sigma B is the permissible bending strength bending stress in the gear tooth material. Above equation is known as Lewis equation. This is known as Lewis equation. The values of Lewis form factors are given in the data book for different types of gear tooths. So generally you have a 14 and a half full depth involute teeth, and also 20 degrees involute teeth, full depth involute teeth, or 20 degrees full subtooth, something like you have three different kinds of gear tooth profiles are there. So based on that, they can easily calculate this Lewis form factor. Okay, so I think I'll stop at this point today. We'll continue this one in the next class also. Okay, in the design of the gears, it is required to decide. Okay, so you are designing a gear train means, so you need to decide which one is the weaker. That is, either pinion is weaker or gear is weaker. So once you identify the weaker one, always we need to design for the weaker one. So that is again based on this beam strength equation. Anyway, we'll discuss that one in the Monday class. So I'll take on Monday, I'll take first hour as well as second hour also. So in that class, we'll discuss about this beam strength, and then we'll discuss about the weight strength also. After that, we take up some numerical problems. Okay, right. So I'll stop at this point today. We'll continue in the next class. So attendance sheet is already placed in the classroom. So those who attended the class, just give a response to that attendance sheet, and then you can leave the class. Or if you have any doubt, then you can ask also.